Like,
All right, we're up and running here.
each part was 15.
Any questions come up the last time?
Um,
What is your question?
We're
I'm
not.
asking what's the question, so we're just out. Last time I wanted to just make a couple more comments on the Jacobian. To finish up, we didn't quite finish. We had over a nice region, a double integral of some function f of x, y, dA, where you're adding up little rectangular boxes in x, y space, all this is like dx, dy. You can rewrite it as the double integral over the region whose image is R, where phi of s is R, of f of x of u and v, y of u and v, a new set of coordinates, dA uv provided what?
Multiplied by the
We call the absolute value of the Jacobian, which is d xy duv, right? And the Jacobian, sometimes called J for short, is just a determinant that you get by taking, so this means absolute value here, but this means determinant here. dx, du, dx, dv, dy, du, dy, dv. And in the special case of linear transformations where x is au plus bv and y is cu plus dv, just number times u plus a number times v in each equation, this Jacobian comes out to be a constant because all these partial derivatives are constants. And this is just a constant magnification factor. So you're just converting this integral, integrating over these little rectangles in here, integrating over rectangles in here with a magnification factor that is the difference between each rectangle here is mapped to a parallelogram in this plane, in the UV plane. And it just scales it so that the area here is scaled correctly to get the area here. However, more generally, even if it's not a simple linear transformation, locally it's approximately linear, and consequently the limit of the sum is still the same as the limit of the sum. So this works quite generally when you have continuous partial derivatives and in some other cases. And you have a nice region. So that was for 2 dimensions. Then also, what about 3 dimensions? In 3 dimensions, if we had a triple integral, if the book likes G, maybe I should use G, I used R last time, but a triple integral of f of x, y, z, dv over x, y, z space, right? Where this notation means the limit of the triple sum, if you will, of f of x, y, z in each little sub rectangular parallelepiped times delta x, I, delta y, j, delta z, k, all added together, limited number of regions goes to infinity, can be written by a similarly this triple integral, where you like to think of these as a transformation of coordinates between UVW space and XYZ space. When these have continuous partial derivatives and the boundary of the region is nice, provided you put in the Jacobian dxyz duvw, and the transformation law looks just like what you did for U substitution. This all on, yeah, okay. In 1 dimension, this reduces to a 1-dimensional Jacobian, which is just dx du. Is the corresponding thing in 1 dimension. So all we're really doing is generalizing the U substitution rule for these integrals. Here, again, if we call this one, H or something, then phi of H, image of this region H has to be the region G. And what's more, you also need, what does the Jacobian need to satisfy? Jacobian has to be of one sign, positive or negative on the whole region. So the Jacobian is never equal to 0. And in the three-dimensional case, you have a three-dimensional determinant. The x to u, the x to v, the x to w, and all the other obvious ones. Same thing here, but y on top. And same thing here, but z on top. And the determinant was more complicated to calculate. Now we could calculate the Jacobian for some of these coordinate transformations we did. What is the Jacobian for spherical coordinates? For the UVW, I will write rho theta phi that we're used to. X is rho cosine theta sine phi. Y is rho sine theta sine phi. And Z is rho cosine phi. What's the Jacobian of this transformation? After all, if we wanted to convert from rectangular coordinates to spherical coordinates, what should we put in here? You know, we already did it actually. That's how you get it. You just calculate the Jacobian. I'll write the short notation here. Is a parcel of x with respect to rho, parcel of x with respect to theta, parcel of x with respect to phi, parcel of y with respect to rho, theta, and phi. Parcel of z with respect to each. Now let's see what we get. If x is rho cosine theta sine phi, and I take partial with respect to rho, treating theta and phi as a constant, I think I better put this in the next row, the next line. Then I just get cosine theta sine phi. If I take partial of x with respect to theta, treating rho as a constant, I get, and phi as a constant, I just get derivative of cosine as minus the sine. So I get minus rho sine phi as theta sine phi. Then I take partial of x with respect to phi, I just change the sign to a cosine. I get rho cosine theta cosine phi. There's the first row of my matrix. Second row, partial y with respect to rho. Well, this is 1 times sine theta sine phi. Partial of y with respect to theta, that turns this sine into a cosine. So I've got rho cosine theta sine phi. Rho and phi are considered constants. Partial with respect to theta is then just cosine theta and everything else you had before. Partial of y with respect to phi turns this sine phi into a cosine, and you get rho sine theta cosine phi. Finally, the last row of the determinant here. Partial of z with respect to rho is just leaves cosine phi. Partial of z with respect to theta, theta is not there, so it's 0. Partial of z with respect to phi is just minus rho cosine, minus rho sine phi then. So there's the determinant I have to calculate. And what can I do? If I use the classical expand in the first row, then I'm gonna get this one. Cosine theta sine phi. Times the determinant gotten by wiping out its own column, so I get this. Well, what's that determinant? Take this times this minus 0 times this, so it's just this times this. I get minus rho squared cosine theta sine squared phi. So I did quickly, this determinant is this times this minus 0. Times that is this. Then I have to subtract off the second element, which is minus rho sine theta sine phi, multiplying the determinant gotten by wiping out its row and column. So I wipe out its column and this row. And let's see, I've got this times this minus this times this. So I got minus rho sine theta sine squared phi. This times this, and then minus this times this is minus rho sine theta cosine squared phi. It's kind of complicated. And then finally, plus the last, so that was this element times its corresponding subdeterminant. Then I take finally plus the last one, so it's plus minus plus on this calculation of determinants. This one, rho cosine theta cosine phi, multiplying the determinant got by wiping out its row and column, leaves me with this one. That one is this times 0 is nothing, minus this times this, so I get minus rho cosine theta sine phi cosine phi. There's an example of calculating the Jacobian. Bring this back. Maybe I'll just move it out so people online can still see. I think that'll be all right. Okay.
Go over like the matrix right there again, like the row and column deal.
Yeah, I take the elements in the first row. This one, this one, this one. I take this one times the determinant gotten by wiping out its column and row. That leaves this part. Maybe I should write an intermediate step, huh? We could do that. Let's write this out. I almost did this. Spent dwelling on this too long. So it's the first element, cosine theta sine phi, times the 2 by 2 determinant. That's how we define the 3 by 3 was in terms of 2 by 2. Got by wiping out its row and column, so it leaves these 4 elements. Rho cosine 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 0. All right, so we take this element, wipe out its row and column, take these 4 elements. Rho cosine theta sine phi. Rho sine theta cosine phi. And then this one, 0, and minus rho sine phi. All right, so first element times its subdeterminant got by wiping out the row and column. Then minus, we said last time, the second element here, minus rho sine theta sine phi, times the determinant gotten by wiping out its row and column. So you wipe out this and this, and you have these 4 elements. This element, wipe out its row and column. So sine theta sine phi here, and then this one, rho sine theta cosine phi. And then, this one and this one, cosine phi minus rho sine phi.
Oh, you're just breaking it up, okay. You're like breaking it up in like
Yeah.
3 pieces.
Yeah. That's the rule. Maybe I should write it down again. For calculating a 3x3 determinant, I was thinking I'd skip over that, but that's probably not a good idea. This is the rule. You write it as 3 2x2 determinants. You take all the elements in the first row plus, minus, plus, and each one multiplied by a subdeterminant got by wiping out its wrong column. So for this one, you wipe out its wrong column, you have these four. A22, A23, A32, A33. That's what I did here. This one times this subdeterminant. Then you take minus this one times this subdeterminant, wiping out its wrong column, you got these two. A21, A23, A31, A3. And then plus this one times its subdeterminant, wiping out its row and column. 2, 1, 2, 2. 3, 1, 3, 2. So that was the way the 3 by 3 determinant can be defined. I think we mentioned, you might say, why do we have to expand on the first row? Maybe we could use the other rows or columns, and turns out you can. You can also take the third row, this one times its subdeterminant minus this one times its subdeterminant plus this one times its subdeterminant. You get the same result. And you can even do it with columns. You can take this one times its subdeterminant minus this one times its subdeterminant plus this one times its subdeterminant. The only qualification is if you pick an even row or column, you have to go minus plus minus instead of plus minus plus. If I expand on the second row, I take minus this one times its subdeterminant plus this one times its subdeterminant minus this one times its subdeterminant. But what everybody does in practice is use the first row. It's just common. So that's what I did here. This is the common way of defining it. There are other ways of defining it too. So that's what I did over here. And now I need one more term here. This is first element times its subdeterminant minus the second element times its subdeterminant. And then there's plus the third element here. Rho cosine theta cosine phi has to multiply the determinant. I'm sorry, it's getting messy here. How by wiping out its row and column, making this stuff. Sine theta sine phi. Rho sine theta cosine phi. And then this one, cosine phi and 0. There it is. There's writing out the determinant formula. Looks like that. Number times determinant minus number times determinant plus number times determinant. And then when I do this determinant, it's this times this minus this times this comes out to be this. This one is this, the diagonal minus diagonal again, it's that. And then on the last one, diagonal minus diagonal is just stuff. All right, now let's bring that back up here. What a mess, huh? Well, fortunately, this clears up a bunch. So now I can say this first one is minus rho squared, cosine squared theta, sine cubed phi. Second one has two terms. It becomes minus rho squared sine squared theta sine cubed phi. That's this one times this one. And then this one times this one gives minus rho squared minus rho squared sine squared theta sine phi cosine squared phi. That's this times this. And then plus this times this is minus rho squared cosine squared theta. Sine phi cosine squared phi. Okay, and now, cosine squared plus sine squared is 1, so this first one actually just comes up, this first two root just come out to be minus rho squared times sine cubed phi. That's this one. And the second two, just come out to be a minus 2 rho squared. Looking awkward here. Oh wait, I'm sorry. No, this is rho squared sine. These are sine squared plus cosine squared is 1 here also. Get minus rho squared times 1 sine phi cosine squared phi. So you use again sine squared plus cosine squared equals 1. You pull out the common factor minus rho squared sine phi cosine squared phi, and it's all times sine squared plus cosine squared is 1. So this one becomes this, and these two become this by taking sine squared plus cosine squared equals 1. Now what have I got? I've got minus rho squared of sine phi common factor all times sine squared phi plus cosine squared phi. That's 1, so I get minus rho squared sine phi is the Jacobian for transformations between rectangular coordinates and spherical coordinates. That should look familiar, right? Hence, this formula we wrote last time, I started to erase it accidentally. If I put it in terms of rho theta phi for UVW, as this Jacobian, as the Jacobian we just did there, J, absolute value, dV rho theta phi. So there's our transformation law to go to spherical coordinates. Well, what's that? Absolute value of this Jacobian just takes away the minus and you get triple integral over the region that you're in spherical coordinates. F of x of rho theta phi y of rho theta phi, z of rho theta phi, times rho squared sine phi, d rho, d theta, d phi is this stuff. Precisely the formula we had before. So with establishing our previous formula that we do with such terrible work, right? We had to draw it in spherical coordinates, draw the little volume element. We could have derived it out of this theorem that's more general. That theorem for integrating in spherical coordinates was just a special case of what we've done with Jacobian. But finally, there's a couple problems in there where they ask you to find a transformation of coordinates. These are sometimes useful in industry if you've got something like an annulus or a parallelogram or something, a shape in something you're building.
Isn't we already derived that once?
Yeah, that was the formula for evaluating integrals in spherical coordinates was you take your integral in rectangular coordinates, you rewrite it like this with this volume element here. They call it sometimes the infinitesimal volume element. Instead of putting d rho d theta d phi, when you convert the integral, you have to put rho squared sine phi d rho d theta d phi. Where did this mysterious rho squared sine phi come from?
Oh, I see.
We motivated with a special region saying the sides are rho cosine phi and sorry, rho sine phi and delta rho going out and rho sine phi along this side, approximately a rectangular box of these dimensions, and then rho at delta theta, and then rho delta phi. Those were the approximate dimensions of the box, and so when you took the limit of the sum, you got this little volume element. We could have derived this just as well by doing the Jacobian first and just putting in this, calculating the Jacobian term, and it was this factor that went in there. We can do one more. We did this one last time. Maybe I'll just remind you just to clear this up. Similarly, in 2 dimensions, this is an easier example. In the plane, polar coordinates. I suppose you want to convert to polar coordinates. What's the factor that go in there? We showed this last time. I just want to remind you. The Jacobian is then dx dr, dx d theta, dy dr, dy d theta. Right? X is our cosine theta. Y is our sine theta. So this determinant is dx dr is cosine theta. Dx d theta is r cosine theta.
Can you move the camera a little bit?
Yeah, I was just wondering about that. I thought I had it enough, but I guess not. Thank you. There we go. So in polar coordinates, partial of x with respect to r is cosine theta, partial of x with respect to theta is minus r sine theta. Partial of y with respect to r is sine theta. Partial of y with respect to theta is r cosine theta. And when you evaluate this, you get r cosine squared theta. And this, minus r sine squared theta. This is r times cosine squared plus sine squared. Is r. again, by the Jacobian formulation, the triple integral, the double integral, excuse me, in the plane of f of x, y, dA in rectangular coordinates over some region R can be rewritten as the double integral over the corresponding region that has that image. F, replace x with our cosine theta, replace y with our sine theta. Put in absolute value of the Jacobian, dA in our theta coordinates. Well, the Jacobian is r, and this is dr d theta, so it comes out to be double integral over the region of f of r cosine theta, sine theta, r dr d theta is the Jacobian times the dr d theta. So we derive the transformation law for polar coordinates by putting the Jacobian here as r, absolute value of the Jacobian. So all those things are special cases, and so what the Jacobian does is it generalizes this coordinate transformation problem. Now, there's a couple problems in there also like this. Find a coordinate transformation that does this. It takes this region R, which is half of an annulus, inside radius 1 and outside radius 2 in the xy plane. This region R, suppose I want to map it into a rectangle. Book writes the arrow this way. I like to write it this way. That's the way most books write it. U and V, where this is a rectangle between 1 and 2, and 0 and pi. You see what the transformation is immediately? What could that be? Once again, the idea in these things is to make the coordinate transformation so you have easy integration endpoints. Here, look, I'm going to have u going between the constant 0 and the constant pi, v going between the constant 1 and the constant 2. You're thinking, what I really want is each boundary here to transform to a constant. Well, this is a constant radius. If I think of that as an arc of a circle, right? That's the idea, this is the arc of a circle. So evidently I want one coordinate to be the radius, and then these are constant angles, right? Theta equals 0, theta equals pi. This is just polar coordinates. What you have is just x equals u cosine v, y equals u sine v. This was just polar coordinates. And the radius going from 1 to 2 is right here. V must be the radius, so I wrote it the wrong way. It should be v cosine u and v sine u. This is the book's example. I put it backwards just to be tricky. So that's the idea. When the constant radius arc of a circle transforms to a straight line, it must be a polar coordinate, right? A straight ray transforms to a straight line. That's a polar coordinate transformation. So that's the transformation, and then you can go the other way. You can put u equals square root x squared plus y, v equals square root x squared plus y squared. Since v is supposed to correspond to radius. And then u is supposed to correspond to angle, so you want tangent u equals y over x. The polar coordinate transformations are what does that. But this is nice when in industry or something, when you're transforming between circles and lines, use these polar coordinates. What's a little harder and also in there is this one. find a coordinate transformation for this one. These are the two important cases when you have arcs of circles and when you have straight lines. There's lots of others you can do, of course. There's some with hyperbolas and parabolas are the main ones that I see elsewhere. Suppose I have this. I went from 0, 0 to 2, 3. Over to 4, 5. And then I make a parallelogram out of it. So I go like this and like this. And let's see, this one went over 2 and up 1. So this one has to go over 2 and up 1. It must be 2, 1. There we go. And suppose I want to transform this into a box. I don't remember the exact thing that the book used, but suppose I make this real easy one, a square, 0, 0, 1, 1. Suppose I want this to be my transformation. I want to take the little easy square, just integrate from 0 to 1 and 0 to 1 of my integration endpoints, instead of trying to integrate over this parallelogram. Can you imagine trying to do this integral on rectangular coordinates? If this is x and y. We mentioned this previously, but I have to do this, right? I have to integrate from here to here. If I have to find the intersection point, it's at 2. From 0 to 2, I have to integrate with this on top and this on bottom, and then from 2 to, these will be right above each other then. I didn't draw it real well. Let's see, so I go over 2 and up 1. No, it went over 2 and up 2. This is 2, 2 here with that. Yeah, this should have been 2, 2. That's what. And what happens here is you didn't have to integrate from here to here. Well, I guess these coincide, don't they? But integrate from here to here with a different thing on top and on bottom. I guess it's drop more like this. So it looks about like that. Here's your region R, here's your region S. What's easier than trying to integrate over these linear functions that are, have variables endpoints is to integrate over just constant endpoints. Here, u goes from 0 to 1, v goes from 0 to 1 if I change my coordinate system. So how do I make this transformation? The trick is to remember that linear transformations are those that keep the origin fixed and transform lines to lines, and they keep parallel lines parallel. So I can just do this by a linear transformation. Whenever I'm taking a parallelogram to a parallelogram with the origin staying fixed, I can always make a linear transformation. So with that in mind, that this is a linear transformation, taking this parallelogram with a corner at the origin to this parallelogram squared, technically, with a corner at the origin, is I'm going to be able to make x equals AU plus BV, y equals CU plus DV, or in this one, they asked you to do it the other way. They said instead of finding x and y as a function of u and v, find u and v as a function of x and y. Well, if it's a linear transformation one way, it's a linear transformation the other way. So this is going to be ax plus by, and this is going to be cx plus dy. We know this works just because it's taking these parallelograms, fixing the origin. Right? So I look for that, and I just have to say, what are those letters that go in there? All you have to do is figure what these letters are. There's actually, I think, 2 ways to do it. You can put this one to this one, or you can put this one to this one, depending on the way you want to do it. But you just have to solve this system. So if I want, when u equals 2, v equals 3 is if I'm taking this point here, a times 0, x equals 0 and y equals 1, plus b times 1. And then 3, the b coordinate here is c times 0 plus d times 1. And so you find out then that p equals 2 and d equals 3. Now with that in mind, we can also then find this one is supposed to map to this one, and then the far one has to map to the far one. Each line segment maps to the line segment. So this one to here, this one to here, these two, and these two all line up. So I can say, how about this one at the point 1, 0? Then I know that 2 for u has to be equal to a times 1. I'm just putting in x equals 1 here, plus b times 0, putting in 0 for y. And then this coordinate, 2 for v, has to be equal to c times 1 plus d times 0. Tells you that c is 2 and a is 1. Tells you that if you have a parallelogram at the origin, you immediately know a, b, c, d from these coordinates. So this one says a equals 2. And this one says c equals 2. And so what we have then is u equals 2x plus 2y, b equals 2x plus 3y, and we should go through and check it. But there'll be the linear transformation in the one direction.
Could you explain the VU graph and like how you would get those values? Like from 0 to 1 and then on the right.
Oh, I just how do I?
Yeah, like how do you set that up?
Corners?
Yeah.
I can pick any rectangle I want with one corner at the origin. Since this has a corner at the origin, I have to have a corner at the origin here. Then I can pick any actually parallelogram I want over here. And there is a linear transformation that will take the parallelogram to a parallelogram with a corner at the origin. So I picked the easiest one I could, the 1 by 1 square, just to make my transformation easy. The idea is whatever, instead of breaking this up into two integrals and having linear functions as the endpoints of the inside integral, this one I can integrate between constant endpoints 0, 1 and 0, 1 and make it an easier integral that way. Now, if you want to go back the other way, again, you could use elimination to solve for the others. If you've seen inverse matrices, all you have to do is write the inverse matrix for this. I imagine most of you haven't yet this year. And I don't think the problem asks you to then convert the other way, but you can actually solve these by as follows. So we'll say to find the reverse coordinate transformation. Technically, the inverse transformation. You can use a little bit of elimination. If you call these equations 1 and 2, you can add a multiple of one to the other to eliminate a variable. So I can take, for instance, 2 minus 1. All right, so if I take u minus v here, that will equal this minus this. The x's cancel. That's why I picked it. If I pick it so the x's will cancel. And then this minus this is 2y minus 3y minus y. And then if I take, to eliminate the y's, I could take equation 2 minus 2/3 of equation, minus 3/2 of equation 1. You take a multiple one add to a multiple the other. And this will eliminate the y's. I'll take this one minus 3/2 times this one makes the y's go away. This one minus 3/2 times this one gives minus x on the right. 2x minus 3/2 of 2x is minus x. And then this one I have u minus 3/2 v. So this equation minus 3/2 the first equation gives me this. And now from these I deduce by multiplying by minus 1 that x equals minus u plus 3/2 v, I equals, minus this one, minus u plus v, gives me the reverse transformation. Oh, that's v, that's right. All right, so that's all in the Jacobian. Last part of the lecture today, we want to do some applications. And then we'll get back to surface integrals next time. I almost did those this time, but I thought that would make too much of a break in what we're doing, so. Applications of multiple integrals. Book writes it this way: if delta of xy is the density, let's say the mass density, of a lamina, meaning an object that's so thin you can treat it as a plane region, modeling it. Then the mass of plane region R is defined to be the double integral of the density over the region. If you think about it, this is just the limiting value of the discrete case. Suppose I had like a population in a plane, right? Like here's Oklahoma City or something, right? And I've got certain density of population. How do I find how many people are in the city? I can break it up into little subregions and take and add up all the people in the little subregions and get the result. This is adding up over the subregions like little molecules or something to make the total density. So this is the limiting case of breaking these things up, discrete cases. And we'll make that definition. Then, if you want to find the balancing point for this, the center of mass, the book will call the center of gravity, which technically isn't correct unless gravity is constant. So I dislike their use of the term center of gravity. We'll call it center of mass. I wrote the main author many years ago. He never responded. I don't know. I like credit him that. The center of mass of the lamina is then this x bar is x bar, y bar, these coordinates, where x bar is the double integral of x times the density dA over the double integral of the density dA. What is that? From a statistical point of view, that's the average value of x. It's the limiting case of some xi, frequency of xi over the sum of the frequencies, limiting case, right? And this is how you would compute like the score times the number of students getting that score, plus the next score times the number of students getting that score. So you're adding up the total scores in the class. If you take the score times the frequency plus score times, this is the sum of the scores, and then divided by the sum of the students in each group is the total number of students. Sum of the scores over the number of students is the average score. So this is actually computing the limiting case of that. It's the average exposition. If you have this density at each plane, at each point in the plane corresponding to this kind of a thing here. Now this would give you, this is the one-dimensional case here that I've written. So it's not quite a complete analogy, but that's actually what it's doing. All right, so there's xi, and then y bar, similarly, is the average mass point calculated by taking the double integral of y delta of xy divided by double integral over r of the density. And it's the average value of y over the region. And what's significant about that is in constant gravity, the balancing point for the lamina. So what you have is this kind of a situation that's really useful in the physical sciences. Suppose I take something that's not very symmetric, maybe a solid or a hammer or something, and I throw it across the room. What does it do? In constant gravity, at least, if you take the center of gravity here, center of mass, then this point actually executes a nice parabola. It follows Newton's laws clear across here and executes a nice parabola. You've been studying that. You treat these things as point objects. The point that does this is actually the center of mass. If you take any other point, then as this thing wobbles around, right, it takes these different positions. And any other position wobbles around that position, right? There's the handle is going like that, and the other end is maybe going like this, right? But the one point that executes the nice parabola in constant gravity is the center of mass. So that's its utility. One of its utilities. We're going to see that there's another useful property it has too. Now, in the special case, oh, one more comment too. What is this thing on the bottom? Double integral with the density. We just call that the mass. When you calculate the average position, exposition of these particles, the bottom integral is just the mass. So you can actually have the same integral in both of these. And the formula is often written like that instead of writing the double integral. I write it this way to show you that it's actually computing the mean position. But you put it M, right? So that's one application. And then there's a special case. Suppose you have an object of uniform density. Delta of xy is equal to a constant k. Now what happens? These become simpler, right? The first one becomes x bar equals double integral of x dA, and I can pull the constant out, right? The bottom one becomes double integral dA, and I can pull the constant out. Well, what happens to the constant then? Because I can pull it out, I can cancel it. Right? And I just have double integral x dA over double integral dA. What's the double integral dA? It's integral of 1, which is, yeah, that's the area. So instead of dividing by mass, you can just divide by the area. After all, the mass is just the area times the density when it's uniform density, right? So the bottom can be written as the area, and furthermore, the top degenerates just double integral of x dA, so it's easier. We'll say that is x bar is the double integral of x over the region divided by the area. And y bar similarly is the double integral of y dA over the region divided by the area. So the center of mass reduces to this in the special case of constant density, which is what a lot of things are, right? Pour a mold with molten metal, it probably settles right uniformly dense object you cast. And now this has a special name. It's called the centroid because it's sort of the center of area. If you're treating the density as uniform clear across, then right, this makes sense as the center of area or centroid. This centroid actually has a number of really useful properties in dealing with volumes and so forth in higher mathematics too. So let's look at a problem here then. Suppose I said find I can't find it now. Find the mass and center of mass. If you have the following region, the lamina's, the density is x plus y, and your lamina, plane region, is bounded by the x-axis x equals 1 and y equals square root of x. Well, I'm interested in finding center of mass for that. I'm going to throw this little flat plate across the room and make the center of mass execute a parabola. What do I have here? Well, the mass is just a double integral over this plane region of the density. is the double integral, and I put in x plus y for the density. And then I can put dy dx or dx dy here, it doesn't matter. I sketched the region in order to see which order is better. Now that I've got y equals square root of x, I know it's this half parabola here. But I only go out to x equals 1. And then I have the x-axis, y equals 0, so I have this plane region right here. I could do this either as a type 1 or as a type 2 region. Let's do it as type 1, then x goes from a minimum 0 to a maximum 1 on the outside. Right, two constant endpoints, and then y goes from the bottom curve, y equals 0, to the top curve, y equals square root x. And there's how I can compute the mass, just as easy as that. Just do the double integral over the region, but insert the density function. So this is the integral from 0 to 1. Integrate x plus y with respect to y, and I get xy plus a half y squared. Treating x as a constant, but y as a variable. I'm going to plug in 0 square root x on that one. Then I'll have to integrate with respect to x afterward. So this is the integral from 0 to 1 of x to the 3 halves plus a half y squared to the x at the top end point, and then 0 from the bottom of this line. I'll wind up with 2/5 x to the 5 halves plus 1/4 x squared. Plug in 0 and 1 and take the difference. It's just 2/5 plus a 4th. Gives me 8/20, and 5/20 is 13/20. One thing to note on these things is since it's a plane region, you have to specify the density as kilograms or whatever the unit of mass is per square meter rather than cubic meter. All right, so this would be a density per unit area. And then if this is in kilograms per square meter, then you'd say this is kilograms. You can also do this with any other density, right? If similarly delta of xy is the charge density, then you double integrate this thing and you get the total charge enclosed. If it's the weight density, you do the double integral and you get the whole weight. So it can be any kind of density whatsoever.
Can you move the camera a little bit?
Whatever quantity density is for. Now that's the mass. Similarly, we can find the center of mass, right? So now the center of mass, x bar, well, in order to compute x bar, I need the double integral of x times the density over the region, right? Here's the good thing about doing these when you do the integral for the numerator in this computation, right? It's over the same region, so it has the same endpoints. So to do this, I did the integral on the bottom to get the mass. And I need to do the integral on the top. I just do the same integral but put x in. So I'm just going to put double integral, the same one I had before, double integral of x plus y dy dx from 0 to square root of x and 0 to 1. And all I have to do is stick an x in here. That's it. That's the integral from the top. So we'll execute this one and say integral from 0 to 1. And integral of x squared then with respect to y is just x squared y. Integral of xy with respect to y is then just 1/2 x y squared. We're going to plug in 0 square root x. Here's the inside integral. Leaves me with integral of x to the 5 halves plus 1/2 x squared. Well, this will again give me 2/7 x to the 7 halves when I integrate x to the 5 halves, and 1/6 x cubed when I integrate half x squared. Plug in 0, 1, I get the difference. I get 2/7 plus 1/6. Supposed to be 12 40 plus 7 40 is 19 40. Yeah. So the x bar, the x coordinate of the center of mass, is just this integral, double integral x times the density, okay, over the region, divided by the mass, we said, that was the formula, is 19 40, what we got for the top integral, divided by 13/20 is the bottom integral. So we get 20 times 19 is, I guess, 380, divided by 42 times 13. 546 maybe.
$546.
Yeah. Then we can reduce that a little bit, I guess, right? 190 over 73. All right, so there's the x coordinate, and then we can do the y coordinate similarly, right? We just take the same integral we did for the mass, but put y in. Yes. Yeah, that in meters then. Yeah, right. And then, also the double integral of the region of y times the density. This is the same integral we wrote before. Is that going to the end here? I guess it's okay. Is over the same limit, 0 to 1, 0 to the square root of x, y times x plus y, dy dx. So we integrate xy, get 1/2 xy squared. We integrate y squared. We get 1/3 y cubed. And then plug in 0 and square root x and take the difference, then integrate with respect to x. Just doing a quick integral of xy is this, integral of y squared is that. We got integral from 0 to 1 of 1/2 x squared plus 1/3 x to the 3/2. Plugging in the endpoints gives us 1/6 x cubed plus 2/9. I'm taking 2/3 of 1 times 1/3 x to the, I'm sorry, x to the 5/2 times 2/5 times this gives you 2/15. So fast integrations is 2/5 x to the 5/2 all times the third. I get 1/6 plus 2/15. I plug in 1 and 0 and take the difference. Yes, let's see, 5/30, 4/30 gives 9/30. 3/10, I think. Yeah, 9/30, and I reduced it now. Okay, in that case, then, y bar is the quotient of this one, 3/10, divided by the mass, which was 13/20. Gives you 60 over 130, or 6/13. Now what you have is this region here, which gets the significance of this. Here at 6/13, so a little less than halfway up, and here at 190 over 273, I'm still a little worried about that one, 190 over 273. You've got a point where if you set it down this way, you can balance it on that spot because it's balancing point. And if you put your finger here, you can balance it this way or here. You can balance it like that. And if you tilt the thing sideways, you can put your finger right on the spot and balance it in both directions. So this is actually the balancing point. 190 over 73, 6 over 13. Balance point. Yeah, that's right, okay. Comments on that one?
So you want our final answer, X bar comma Y bar?
Yeah, this would be the final answer. Right here. I said there's some applications of the centroid also. This is a theorem of Pappus, which goes back, he's an ancient Greek. Says that if you take a plane region and it's revolved at a radius so that it's the resulting volume does not have the cross sections overlap. Then the volume generated is just the area of the plane region times the distance the centroid travels. So it's V equals distance centroid traveled times the area of the lamina of the region. Now, I did this for a circle. Actually, you can do this more generally if you take here's what we had here. We have some plane region. And we take and revolve it in a big circle to generate sort of a solid like that. The solid it generates is just the distance the centroid travels, X bar, Y bar. Times the area of the region, as long as it doesn't intersect it. The plane region doesn't intersect in these cross sections. If you rotate it with a radius less than the distance out to the edge of the plate, then it doesn't hold. But in fact, you don't even have to travel in a circle, even though I used it for this example. That's Pappus theorem, so I stated it that way. But as long as you can travel around an arbitrary path, like a garden hose here, and as long as the hose doesn't have cross sections that overlap as it moves, the volume of the garden hose is the cross-sectional area times the distance to the center of the garden hose went. So it has that kind of theorem more generally. Which means we can use this as follows. Suppose I make the torus where I take a disk of radius 1 and center at 2, 0. And I revolve it around the y-axis in a big circle to create a donut that we call a torus. So here's this cross section over here. Homer Simpson's problem here. What's the volume of the torus? Well, there's a real neat computation you can make for this region here that's a circle. What's a centroid? The centroid is just right as its center, right? And you do that because it's really the center of area. You're saying, what's the balancing point of the disk? Well, balance is right in the middle, right? So that's the centroid. This is X bar, Y bar. What you want to know is how far does the center travel? Well, if it's the distance the centroid travels is multiplied by the area of the disk, then you've got it. But the distance centroid travels, since it's a circle, is 2 pi radius, and the radius is 2. The area is pi r squared. This is 1, so it's pi times 1 squared. And we just get that the volume of the torus is in 4 pi squared. How about that? So there's an application of the centroid. When you make it travel along a path, as long as these cross sections don't intersect, you just take the area times the distance traveled by the centroid. All this stuff carries over into 3 dimensions also. You can do if you have some other big object, maybe an ellipsoid or something, you want to say, well, what's the mass of the ellipsoid? You can take a triple integral and you can find the center, the balancing point, the center of mass for a 3-dimensional object, just like 2-dimensional objects. We'll have to do that next time. Won't spend too much on it because it's completely analogous to this. You use triple integrals instead of double integrals. However, you can do one more step at that point, and you can then do moment of inertia. I'm not sure we're going to do the same things with the center of mass. Try these problems for homework. I haven't got to all of them. I haven't done the 3-dimensional stuff, but you can do all the 2-dimensional stuff, right? 14.8. We kind of squeezed this last one, but 14.8, 1, 3, 19, 21, 25, 27. There's a bunch of theoretical questions in between, but stuff that weren't worth it. They weren't good questions. 37, 43, and 57. These last ones are the theorem of Pappus. The earlier ones are finding center of mass and centroid for plane regions, and then there's some in the middle with 3 dimensions that we haven't done yet. Well, things are getting better. I came in tonight and it was actually light out when we started class, right? So things are looking brighter and COVID's going down. Maybe we'll have a good end of the semester now, I hope, and we'll have lots of fun after. So next time, finish this and do surface area, and we'll be about done with the chapter, I think.
Sir, when is our next test?